Hi everyone. Today we have the privilege of inviting Dr. Amit Sharma from NSR Bangalore to give us a talk at our theory seminar series. It's not really a theory seminar. We have audiences from the CDS division as well as EECS to attend this seminar. Happy to invite Amit. I'll give a short introduction and then we can begin. So Dr. Amit Sharma is a principal researcher at Microsoft India. His work bridges causal inference techniques with machine learning with the goal of making machine learning models generalize better to be explainable and also avoid reasoning errors. To this end, Amit has led the development of the do-while library, which has so many citations on GitHub. This is for causal inference and the DICE library for counterfactual explanations. He also co-founded pairwise, an open source ecosystem for causal machine learning. His work has received many awards, including a Best Paper Award at ACM CHI conference, Best Paper or Honorable Mention at ACM CSCW 2016 conference, 2012 Yahoo Key Scientific Challenges Award, and the 2009 Honda Young Engineer and Scientist Award. So without further ado, I'll hand it to Dr. Amit to begin his talk.
Thank you, Rahul. So this is a very strange talk for me to give. As he was mentioning, I've been working on causal inference for quite some time. And I never thought what I'm going to present today would be possible. So this was a surprise for me as well. I've spent the last 5-7 years telling people that causal inference is a very hard problem. Causal discovery is very hard. You can't just have data and sort of infer relationships, what causes what, and then also maybe make decisions based on that, right? But the last few months, the more I've tried large language models, especially models from OpenAI or GPT 3.5 and 4, most of my assumptions have been disproved. So I used to think that you cannot learn causality just from data. What I'm going to show you is that these large language models are somehow able to seem like they're able to reason causally. So all of this work, I would say, is not definitive. This is more emerging. I'll present what I'm finding with these large language models. But I think the hope is that this is going to take away and start more questions. So how do they do it and what exactly is going on is going to be the theme of this talk. So just a brief primer on causality. Very at a high level, you can think of it as the study of causes and effect, or the study of action and effect. So if you're interested only in correlational prediction, it usually means based on some past data, what would the future look like? So if you have a patient, it just says based on past health data, what's their chance of a heart attack in the next 2 years? Causal prediction, on the other hand, starts to think about how would the data change if some other variables are changed, right? And they're not seen like that in the past. So essentially think of a question like, what should I do today to reduce the chance of a heart attack? Now, what this means is to predict some kind of feature distribution which has never been seen before, right? So this person might not be, let's say, exercising, and they ask, what will happen if I now start exercising? How will my health or heart attack risk change? So that's the sort of, at a high level, what we are trying to do. We're essentially trying to do, you can think of it like auto distribution prediction, but it's also about modeling the generative process so that at any point you can change some variables and ask what would be the effect of that on your outcome. And I mean, this might be true for your field as well, whatever you're working on. These kinds of questions come almost everywhere. Right? So if you're in a business, these days the subscription models are very common. Netflix, any kind of OTT platform has subscriptions. So people there might ask, would this customer discontinue their product subscription? That would be a prediction question. But then you can ask, why did this customer discontinue their subscription? Of course, one answer could be they were not using it a lot. That is one level of sort of why answer. But what we're really looking for are more interesting reasons or more interesting hypotheses on why that might be. I already talked about medicine. You might want to find out what's the effect of a treatment. Again, this is a super important question in medicine because you cannot do randomized trials for everything, right? For many of the drugs, many drug combinations, people are just given those drugs over a long period of time. And doctors or scientists want to retrospectively understand how much was that drug really helpful for patients. Same for social science. I think a perennial question in social science is about influence versus homophily, which basically means like if you have friends, is it because you're influencing their preferences that you look similar, or you actually make friends with people who are similar to you, and it just turns out that the data looks like you both are having similar preferences. And same for policy as well. I mean, another example could be air pollution. You just want to know whether government regulation would lead to a decrease in that. So the reason I was giving you all these broad examples is just to sort of think that if that's the case, then causal models should be widely deployed. Right? Across all these fields, people should be using causal models and people should be making these kinds of predictions with certain confidence. But that's not the case. In fact, I'm in Microsoft, so when I talk to people within Microsoft, that's industry, but also when I talk to people outside, the common refrain is that causal modeling is not practical. And I'll go deeper into that. So that's the sort of state that we were in before large language models. There was a lot of demand, but at the same time, we were not seeing adoption. And for a most part, I think it was because people did not find these kinds of models practical to work. So what we'll do today is look at whether large language models may be one answer to this question, and can they make causal inference more practical? And how I'll do that is I'll first set up the challenges. I'll first break the story of why people think causal inference or causal machine learning, or in general causal modeling, why is it not considered practical? Essentially, there are two fundamental reasons. One is that learning causal relationships is, in some cases, provably impossible just from data. And so often people want to then rely on some human expert and rely on some kind of lot of human priors going into a model, to the point that it's questionable then, like how much is your causal modeling really from data, or how much is it just being driven by whatever human priors are. And the second problem is that more and more the kind of data that machine learning works with is text or images, and we just don't have a good way of representing causal concepts from text. So obviously, it won't make any sense to say this token causes that token, or you want to work at the level of some concepts or some words, and that's a chicken and egg problem. People don't know how to even extract these kinds of things. What we find, though, is that miraculously, or sort of luckily, LLMs are actually good at exactly these problems that we thought algorithms would never be good at. So exactly the problems that needed human input and were impeding causal inference practicality, I'll show that those problems LLMs can do well on. And I say that with a little bit of confusion here, because they can do well, but we don't know how. Right? So that's the kind of interesting question. So on causal discovery, counterfactual inference, LLMs are the state of the art today, but no one knows how. And also they have unpredictable errors. So they might look good to you overall, but then they can fool you as well, very easy. And the future, of course, I think this is something I think this group may be most interested in, is how do we combine these two things? So if you have principled causal models and you have these LLMs giving sometimes nice, sometimes weird kind of output, can you combine these two? And if you can, then there's a big potential to impact exactly all these fields with deployable models. Right now, what we have are really sort of hard to deploy and impractical, quote unquote, models.
What would be an example of counterfactual in the case of LLM?
So it would mean, let's say you're given a health history of a patient, and the LLM might be asked, if this test turns out to be positive, then what would this patient's diagnosis be? And suppose that does not happen, then you can ask, what would have happened if this patient was given a different treatment? So it's essentially the normal counterfactuals that you and I talk about in English, but I think the LLM is able to process.
All of these applications are enough practical significance. It's not just a matter of complication and an understanding. Or the literary. So even having medical trials or advertising, people would be happy to invest in money to get these. But you're saying in some cases it's not.
I think where they can do randomized experiments, they do, but that's model free. Like they keep doing more and more experiments. The problem in these kinds of scenarios is that the model building is an initial step. So it's like an initial cost you have to take. And in my experience, the conversation goes like, if you want to do causal modeling, the first month of our collaboration, we're going to spend just building a model manually, talking to it. And somehow that just doesn't fly because people are unable to see the potential of this technology without having to spend a large amount of their effort doing manually. So I think that's been just a psychological impediment in talking these things.
In causal modeling, let's say there's a causal hypothesis. There might be some way of verifying that, and that's why you said that causal modeling is hard because the verification of your hypothesis is hard.
Yeah.
But somehow LLMs are able to do that without touching the real code.
Exactly. Yes, that's the mystic results that we are finding. So let's come down to now the basics, right? I want to set up these fundamental challenges, tell you why they're mathematically hard, and then we'll actually see how LLMs are able to somehow sidestep this impossibility results and still do something useful. The two challenges, as I mentioned, one is learning causal relationships. So this is not even about building a full graph or building a full generative model of your data. This could be as simple as I give you two variables and I ask you which one causes what. So imagine like the canonical example is altitude and temperature. So I give you two readings. One is the altitude at different places and the other is temperature. Both might be varying, of course, and I would ask you which one causes. Yeah. The second is how do you represent causal concepts? Machine learning, as you know, has taken great strides. I think now people don't even think twice processing images, processing text, and so on. But again, in causality, it becomes hard because what will build the graph over? If you're given just a text like this, which is a patient's description of essentially what they're going through, their symptoms, extracting even the right level of variables to construct the graph is quite hard. But you want to think of it mathematically, this is the fundamental problem. That was more an empirical problem. People are not able to solve this. So here's a quiz, right? This will sort of get you to just imagine how difficult it is to infer causality. So suppose I give you this data. This is about two variables. And from 2000 to 2010, about 10 years, you see an almost perfect correlation. So if I told you that one of them was computer science doctorates being awarded, and the second one was computer science research jobs in the US, you would say that makes sense, right? And these two might be actually causal in some ways. Maybe there are more jobs, and that's why more people are taking up PhD programs, or the reverse. Maybe there are so many PhD students, and so somehow there are more jobs getting created. But actually, that's not true. It happened. Some economists did not like that theory. But now we're back. But actually, that's not true. This data is real data. And this is about computer science doctorates. That was true. But the second variable is total revenue generated by arcades. Completely unrelated. And you and I can think about that because we have some knowledge of what arcade revenue means. It's gaming revenue. So most likely there is no causal relationship. Maybe the US economy is going up, and that's why this is what you see. But my point is, if I just give you this, and if you are a very good, faithful data scientist, what will you do? Based on if I just change the variable names, you're going to get different conclusions. So this is kind of a very intuitive check on how hard it might be to infer causality. Mathematically, people have also shown that it's provably impossible. If you're just given two variables, let's say A and B, so this is the arcade revenue and doctorates, you can think of it in terms of factorizing the graph or factorizing the distribution. So the general distribution, observed distribution you might have is the joint, which is probability of A and B. You can factorize it either as probability of B given A, which would mean that A causes B, or you can factorize it the other way, which would mean probability of A given B. Now, if you run maximum likelihood on any of these models, you essentially get the same likelihood. So impossibly, unless you make any other parametric assumptions, if you're just in the completely non-parametric world, you can show that you cannot actually distinguish between these two just based on data. And in practice, that's not even the problem. The problem is that there could be a third variable as well, which you don't observe. And that variable actually is causing all the correlation that you see. So it's not even that A causes B or B causes A and B could be completely unrelated. And that's probably what was happening in an arcade exam. And just to give you an overall background, there's been so much work. There's been like 20 years of work on solving this problem, because you can always think of ways or assumptions under which this problem may be tractable and then develop algorithms. So one option is that you do full graph discovery. And there people have found some graph structures which are testable. So I think people might have heard of this from Julia Paul's work, but this is a very simple result which shows that we have 3 variables. Then the first 2 admit the same kind of independence relationships. But the last one, which essentially says that 2 variables cause this 3rd variable, in that case, you get a special pattern. And so you can actually say that those 2 variables that cause 1 variable are independent. Whereas in these other cases, because you either have a chain of causality going through or a fork, the independence is always conditional. Again, you don't need to go into details about this, but the basic idea is that there have been ways in which people have discovered certain graph structures which can be isolated from data. But often what happens is your full graph is not made of these structures. And so ultimately, you still get some kind of equivalence class. So you can distinguish between some models, but more or less, you'll have a large class of models which you cannot distinguish between. And so there's been more progress. People have tried, for example, faster conditional independence tests. People have tried non-Gaussian assumptions. Somewhat surprisingly, if you have a linear model with Gaussian noise, it's not identifiable. But if you have a linear model with non-Gaussian noise, somehow the causal graph can now be identified, which means you can have a unique causal graph for that problem. But again, you can think about it, right? I mean, all of these assumptions may or may not be true in your data. And many of these don't look for unobserved confounding anyways. So what has really happened? Oh, there's a 3rd group of methods as well. Actually, this is very popular these days. So this method, how I describe it as, use deep learning and hope that it works. So they have no identification results, but they somehow say that there's a continuous optimization problem that you can define. And that sometimes gives you interesting results, and sometimes it can give you wrong results. First of all, they're not identified, right? So it doesn't work. You'll get just an equivalence class. But they're also very slow, because given a data set, let's say with n variables, you're searching over all possible graphs of those variables. So it's a discrete optimization problem. And so all you can do is maybe have some score for each graph and then try to maximize for that score. These people found that there's a way in which you can represent the graph using a matrix, essentially an adjacency matrix. And a condition on that adjacency matrix can ensure the acyclic graphs to emerge. And so now you're just doing a continuous optimization on the parameters.
So somehow conditional independence test equivalent to finding the joint distribution, or are they another? So because the previous graph you spoke about conditional independence relationship, and before that, let's say you can from data only observe the joint distribution. Are they equivalent for very large?
No, they're not equivalent. So this is a good example, right? These are 2 structures. One of them is a chain, basically B causes A causes C. The other one is different, right? A is causing both B and C. So these ones, I think the joint will be the same. You won't be able to distinguish, but the graphs are different.
But the independence tests are
also the same, yeah. So yeah, that's true. If you have all the independence tests, then you have the right joint. But that itself is not enough to give you the right graph structure. For the same joint distribution, you can have multiple graphs.
So for joint, you can imply all the independence conditions, but not.
Yes. And so all of this I was just trying to display is that it's been a very hard problem. It's taken people 20 years to come to some solutions at least. But then there have been like 3 papers in the last 3 years where people said, we've done all this progress, we have all this theory and algorithms for solving this problem. Let's just try it on a few real world data sets. So I think one of them was a medical data set that they tried on. They actually had doctors make a graph for them and give them data. Similarly, they did one for climate science, and I'll talk about those data sets as well. And the same thing they did, they asked the climate scientists to create a graph of their data. But when they compared even the state-of-the-art discovery algorithms on these data sets, they found that the results are far from satisfactory. I mean, they're not even usable. They're actually very bad, to be honest. And so that's the state, that was the state of the art until large language models came. And people usually used to think that this problem is very hard. And so the best option that you have is just manually construct your graph. And to make matters worse, the way causal inference works is that all the downstream analysis that you do depends on this model. If you're familiar with Bayesian inference, think of it like a prior. But essentially, this prior effect stays even if you have infinite data. So based on what graph you have, will determine what results you get. So if you're doing effect estimation, which means how much the A cause B, or if you're doing counterfactuals, what happens if A is changed, or if you're doing attribution, why did this change? I lost all my subscribers, what happened? All of these questions ultimately depend on the graph. So if you get the graph wrong, then you also will get the answers to your questions. So now that the graphs are hard to learn, it's also that knowing which variables to create a graph on is also hard. And historically, people have not even looked at this question because the tabular data graph discovery was so hard. People did not even think about these kinds of questions, right? What kind of questions? When I give you just this large text written by a doctor about a patient. The doctor is saying, blah, blah, this patient has this disease, they have come up with this symptoms, and I did this test and I found that this happened, right? Whatever, they keep writing. So if you want to really assist doctors using machine learning, what you want to do is to first extract the variables here, and then maybe create some kind of relationship between them, right? So what people have done for sure is what variables are mentioned in the report. You can do these kinds of models, which will tell you, oh, this doctor is talking about this patient, this disease, and so on. But then this question of what variables should the causal graph contain is unclear. Right? So one, of course, you can say mentioned in the report, whatever names are mentioned, I'll use them as variables. But actually, there are lots of variables or things which may not be in this report and should also be in your causal graph. It's very hard to know just from looking at this report what those should be. And also, you should also think about like what should be the right level of this graph. Should it be at the level of diseases? Should it be a level of tests? And so on. So all of these are very vague questions that people thought best not even to tackle in these scenarios.
Also, the ground.
Exactly. Yeah, that's also true. Yeah. So even if you get multiple doctors to create a graph, they might differ, right? And so maybe there's also this question of to what extent are graphs useful. Perhaps they're just best abstractions to give you some decision that you want. And so exactly, I think these kinds of questions were people were not even touching them. So.
Yeah, so I think to add to his question, so there will be an equivalence class of graphs that give you the same decision.
Yes, yes.
And discovering one of them is sufficient for you?
Is sufficient. So typically, that's how people think about it from a practical perspective, at least, which is that you ultimately need to make some decision or you need to give some recommendation to someone, right? Based on your data analysis. As long as your graphs admit the same kind of decision, they're all equivalent. Okay. So one of the reasons I'm just setting up the stage was to convey to you that people like me have been working on this problem, and it's a hard problem. It's not just I'm showing you a math problem that LLM has solved. I'm not showing you like a coding challenge that LLM has solved. I'm really showing you a key scientific challenge of this day that LLMs are somehow able to get good answers. So this is what we'll do. We'll take these transformer-based generative language models. They are trained on a very simple loss, nothing to do with causality, just predicting the next token in the large amount of internet data that they have. Some of them are also fine-tuned and following instructions. That's one detail. And we'll try to see models ranging from small size to large as available today. So ADA is a model from OpenAI, which is about 2.7 billion. When it was released, I think language models were not the craze. It's quite simple model. But then we also look at GPT 3.5 and GPT 4 as well. And so our question is, as model size increased, a lot of people have said and observed that language understanding increases, programming knowledge increases, creative writing increases. So we were thinking of causality. What would happen? So in fact, the story is that one of my colleagues sort of asked me to check this. And my initial reaction was, this is not going to work. Why are you even asking me to check this? Causality is such a hard thing. But ultimately, I checked it. And I'll show you some of these explorations that I was doing initially. So I said, OK, if people are saying this can work, let me try it. So I'll give it an example, which is very common. It's very common if you've read Yuria Pearl's book or even blogs on causality. People come up with this setup where there's rain, there's sprinkler, and there's grass. And obviously, the right answer is, if you want to get a graph, the rain causes wet grass, and the sprinkler obviously can also cause wet grass. So I just write this and give it to GPT-4. Here's the output that it gives. Two things to note. One, that its answer is correct. It does get the right answer. You can see it. I can find. I'm just confusing my hands. This is the graph, and this is the answer. I think it's the arrows in that thing. Oh yeah. Yes. But you can also see the explanation. So it's not just like a predictive engine. You can look at the first two paragraphs which it writes. So it does somehow can utter that rain can cause the grass to be wet, and the sprinkler is on, it can also cause the grass to be wet. So you can see two things which are good here. One is you get the right answer, and you also get a human level explanation of what the model might be doing. And that's great. But I think if you're a skeptic like me, you would say, well, this example is so common, it's in textbooks. So it might even have been in GPT-4's training data. So how is this impressive? I just learned to write the right answer. So then I started doing some interesting changes. So for example, you can make grass to be grown indoors. It's not that common, but some people do it. So I just add this one phrase. Everything else is the same. I just say that grass is grown indoors in a closed room. But this has never been seen by GPT-4 for sure. But if you look at its response, kind of interesting. It does get that rain cannot directly cause the grass to grow indoors. I mean, it cannot make the grass wet because the grass is indoors. But then it makes some weird theory about how rain can still affect if someone decides to turn on the indoor sprinkler, because it thinks there's some moisture, right? There's some moisture outside that can make your grass wet or whatever. Right? So still, I would say it's still not bad, right? I mean, if you think about it, it's not perfect, but it's also not seems like it's just memorizing things. It is able to do some kind of generalization, and it's even able to sort of bring up theories to a level which are plausible, but maybe not correct. And so, I did a lot of such experiments. In fact, if you're curious, you can also try whatever is your domain of expertise or whatever your questions you have. I would encourage you to try it with the LLM. It sometimes gives very interesting answers that make you think as well. And so for me, yeah.
Not a pretty good system point of understanding. Like, these are language dependent in the sense that if I were to give three abstract names, like of diseases that are, I just take three diseases and spell them out in Sanskrit.
Yes.
And then ask like this, that would not work.
That would not.
So it's not actually data driven, it's more language driven.
Yes, yes, yeah. So I think previously there used to be these kind of knowledge-based discovery agents. And I think this is closest to that. It's kind of a knowledge base which it's operating on. And so any concept that can be expressed in, let's say, English, it would do well on. But if you just give it ABC, it has nothing. It cannot do anything. So yeah, so I think as Siddharth is also pointing out, right? One thing you can immediately see is that if you just give ABC, it won't work, right? But what about other things, right? How robust is this capability? And if it is robust, then how is it doing it? Both of these questions we wanted to answer. And so with my colleagues in Microsoft and also University of Chicago, so Emre Kachuman from Microsoft and Robert Ness, and Chenhao Tan from University of Chicago, we kind of banded together and said, can we just do some experiments first empirically to see how robust this is? And if it is, then we'll also try to build some hypotheses on what might be going on.
Can it be discovery in cases where only causal algorithms can discover the causal graph? So if you so if you give some variables and some data between those variables, and the causal graph can be inferred, will it infer it, or only things it has heard a lot of?
Think of it like two completely different complementary skills. The causal discovery algorithms ignore the column names. They will just look at the data and give you an answer. LLM will ignore the data. It will just look at the column names and give you an answer. So in some cases, they might be combined. They can be combined very fruitfully. And people are coming up with such algorithms. But in this talk, what I'm going to show is that even if you just trust the LLM, you can sometimes get very good results, those rivaling what you will get with data. So that's what we did. Basically, we said we'll take some of the hardest benchmarks available today for discovery and just write a prompt, some amount of decent prompt engineering we did just to write a reasonable prompt and ask it to either do pairwise discovery or full graph discovery. And let's see what happens. So the first thing we did was take this so-called Tubingen benchmark. It's a benchmark from Moich et al., where they manually created a set of pairs which they knew the right causal direction for. And one of the nice things they did was that they took it from multiple domains. So you can find examples from zoology, the age of an abalone and shell weight, to physics, which I don't understand, but there's some PPFT and net ecosystem productivity, and also cognitive science and atmospheric science, engineering, and so on. This was kind of the perfect data set because they had names which are actually real-world concepts. And they also had data for it. So there were lots of benchmarks already available on how good you can do on this pairwise stuff. And most existing algorithms were achieving about 80 to 70% accuracy. I think the best reported is 83% on this data. So we thought, let's not look at the data. What we'll do is we'll just take these column names and write a prompt for this LLM. Right? So how the strategy would work throughout this talk is that we are going to ask the LLM as if you'll ask a person to just tell me which direction causality is. That's all. So first we tried this 2 prompts per pair thing, where we would just ask the LLM, does change in A cause a change in B? Please answer in yes or no. Very simple. And we can also ask the opposite and then take the average of whatever answers it gives. For example, I can ask, does changing the alternative cause a change in temperature? Please answer in a single yes or no. As I think we got slightly more sophisticated in prompt engineering, this is not the best of times to do this, but I think we kind of spent some time just thinking about what might be the right way to ask this question. So we came up with this long thing where we ask both questions at once. We just say which cause and effect relationship is more likely, A to B or B to A. And then we also ask it to work it out in a step-by-step way. I think other LLM literature has found that if you ask the LLM to do something in steps, its accuracy increases. And then we started getting some responses from this LLM. So right off the bat, I want to tell you that this is not something that's trustworthy. This is a simple example. In one case, we were asking the LLM the age of an abalone and the length, which one causes what. And the second case, we just changed the length to diameter. So now we are asking the age of an abalone stays the same, and the output now is the diameter. And you can read this response, but I think in one case it gets it right, that changing the age should change the length. In the other case, it gets it wrong, exactly wrong, saying that changing the diameter should increase the age. And of course, you can now debate about whether age itself was clearly mentioned or not. Maybe we should have made these variables more clear. But the basic insight is that these models work, but they can also just give any answer, which might be possible, right? So in some cases, they are probabilistic.
This is just pre-trained LLM, or will you fine-tune it for?
This is just pre-trained LLM. This was GPT 3.5. So we are doing, actually, from a technical standpoint, we are not doing much. We are just writing an English prompt, giving it to a pre-trained model, and just recording the answer that we get.
Do you think like a few shot might?
Few shot definitely would help. We did not try. I think there are other papers now which are trying it, and it would help. In fact, specifically, if you have a domain in mind, like if you have, let's say, an astrophysics or medical domain, and if you give examples only of that domain, that's. So let's look at some numbers. As I told you that most algorithms that use data, the max was about 83 accuracy. The first thing we saw was that models of a lower size don't really work. So ADA to about DaVinci to about text DaVinci is 0.02, 001, you're getting about 50% accuracy, which is what you would get if you randomly guess. But something interesting starts happening around the 170 billion mark, text 17003 and 2. Somehow we reach 80% accuracy just doing this simple thing. No idea what's going on, but that's not bad. But then we started slightly changing the model's prompt itself. And so there's something called a system prompt in LLMs. It's essentially like a meta prompt that you can write. So we just added something like you are a helpful assistant for causal reasoning. What this does mathematically is that just makes the conditional distribution of the generation to be conditioned on this text, right? So it probably then is behaving as if it's a causal inference book or whatever, and going more into the proper distribution of those kinds of texts that's seen on the internet. And that we saw was very interesting. It just increased the accuracy to about 86%. 5-point jump from GPT 3.5, which is ChatGPT, just from this one line. And then we tried a single prompt strategy and we got further gains. And then finally, when we got access to GPT-4, we just tried it once with a single prompt. And I don't know what is special in that model. It has obviously a lot of parameters, but it got about 96% accuracy. So I think what's surprising is not that these LLMs are able to do it at all, this task. I think they can with some accuracy. What's surprising is how high this accuracy is, even though we know they probably have no causal model of the world. And so as I was saying earlier, we should think of these as complementary methods. One is covariance-based and one is knowledge-based.
The 4% where it fails.
Yeah.
On that condition of that, like how does the
Oh, we did not check that. That would be interesting to check. But I think that also depends. Some of these things depend on how you name these variables as well. So
yeah, it's fine. But I'm just wondering if I look at maybe the answer is both.
Yeah, that is true. That is the right answer.
So yeah, this is like for the 4%, what is the is it still like I just focus on those examples, what do I apply to the
Yeah, so I think some people have done the opposite. So there's this LM prior paper that also used this data set. They first used the database method and then used LLM to increase its accuracy. So there they found they were able to increase accuracy by 5 percentage points. I think what you're asking, people are trying it now. I don't think I have results. But that definitely is the way to go. I think what we are currently showing is just LLM only. What's the max we can push it? But yeah, ultimately you would want to combine, or at least think of it as a prior at least. This could be a good prior.
So the example that you gave earlier, indoor was definitely out of distribution.
Yes.
But is there any chance of this being in distribution?
This is in distribution. So I'll give some results. We also checked that. This has been partially memorized, and that could explain high accuracy of LLMs. And then there are some specific things that you can actually sometimes be amazed at just how much this model knows, right? And again, I'm using knows in quotes. I don't know what it exactly is doing, but we asked it the question ozone concentration and radiation. That's in the data set, and we got a wrong answer. And I read the answer and it kind of made sense to me. So I was wondering, like, what's going on? And then when I looked at the data set in detail, I realized that the data set was mentioning ozone concentration at ground level, whereas the LLM was answering ozone concentration at stratosphere level. And of course, if you kind of give it that, it's the ozone concentration at ground level, it will give you the right answer. And so then, of course, the questions were twofold, right? One is what Rahul is asking. Is it just in distribution? Is it just a memorization game? Or is it something real? So we tackled it in two ways. One is I'll show you multiple data sets where we tried exactly the same thing and what kinds of results we get. And then lastly, we'll also check exactly that problem head on. The question. Yeah, I think it's an open question right now. I think people don't understand this. The best test would be completely out of distribution data. So let's say you describe, I don't know, some different planet where different rules apply, and then you ask the LLM to infer what will happen in that scenario. Those kinds of tests might be the most strict to actually check whether it's following causality or not. But then again, it's hard to construct those tests because you give away a lot of information in the prompt itself, right? So then you could also say it's just learning from the prompt. So the rain example I showed you was one creative way to test this, where we just made the grass indoor. But I think there hasn't been a systematic way yet. People haven't found it. Yeah. I think if there are a lot of such examples and all of them work perfectly, then yes. That's the only way we can test these models because I mean, they're not interpretable. They're not even available as full parameters. The best you could do is just behaviorally test whether they're able to pass whatever is the basic outer distribution examples. Actually, the other way, I'll just maybe talk about that right now because you asked this question. The other way of thinking about it is the following. If there is a model that has memorized all of human knowledge and it gives you useful answers in distribution when you ask it things about the world, that's not bad. I mean, at some level, I don't care about memorization. Like if it can memorize everything and answer my questions in English, good. At least the people in practitioners would love it. Scientists, of course, would want to answer why it works. But I think that's the other way of looking at it. If it can have the entire world's knowledge in its training site, then all power to it. Do memorize.
All the distribution set is empty.
Yeah. So let's quickly go through some more examples, but I think the same kind of patterns you've seen. So this is also, this dataset was chosen because it's not common. I think it was released only in 2019. It's not even publicly available. You have to kind of write some code to generate this dataset. So we thought this might be harder. Again, not impossible, but harder, unlikely to be in the LLM space. And it has examples of names which honestly I don't even understand. But you can think about it as radiculopathy is some kind of spinal sort of nerve damage. And lumbago, for example, is back pain. And there are lots of such variables that this data set has. We tried the same thing. Right? No brains. We're not applying our brains at all. We just tried the same thing. And we found the same result. Like smaller models don't work well at all. But somehow GPT-4 and GPT 3.5 start giving interesting results. GPT 3.5 gets about 85% of these correct, and GPT 4 gets again somehow 96%. And sometimes you also get results which tell you the limits of building a graph itself. Right? So here, for example, the LLM was saying that radiculopathy can cause obesity. The doctors who created the dataset did not think so. But when I searched Google Scholar, again, I'm not an expert, but I did find some papers which said that sorry, the other way, obesity may be a risk for radiculopathy. So then you might think pairwise discovery might be very easy. Let's try full graph discovery. Now I have 10 variables, I have 100 variables. LLM, give me the graph. Okay, we tried a subset of that as well. So this data set also had a special small variables set of variables, just 100. 50 of them are true correct edges, 50 of them are not edges at all. So now you need to infer both the existence as well as the direction of an edge. And so we slightly changed our prompt. Basically, earlier we had two options, now you have a third option as well. The LLM has to answer A causes B causes A, or there's no relationship. That's the only change. And now on this data set, at least we can start comparing earlier work. So this paper from Tu et al., who also are the authors of the original data set, explains what they had done with ChatGPT. So they did something very similar to us, but their prompt was just one line, very simple prompt. That's A cos B or something like that. So they were finding that about 0.21 is the F1 they can get on getting the correct edges. And if you do random, actually you can get better than that. You can get 0.33 if you're just randomly selecting the edges. And here what we found was that the prompt that we used for the same LLM was able to increase the F1 by about 3 times. So a couple of insights here. One is that these LLMs are very finicky. It really matters how you ask them the exact same question. There's some art and science there. I think this can also be improved further. We just did not spend enough time improving it. And the second thing is that LLMs can also generalize to non-existent edges as well. So it's not just pairwise. In fact, we are now doing some experiments where you can take this to the extreme level. Right? If you have a graph of n nodes, just do n square pairs, ask all of them to the LLM, and see what kinds of graphs you get. Right? That's something that we're currently doing. But this is something that can be scaled very easily. Yeah.
So this additional part which is prompts, are they same for all of the examples, or are you tuning?
Yeah, they're the same. I think the only thing you change is these templates, which takes the variable names.
And this can also be generated by.
Yes, I will come to that in the next part. It can be, yes. We did that in some other experiments. The final data set we tried was in atmospheric science. So this data set was nice because it was very small. So only 12 variables and 48 edges. So we could run the LLM on the entire set. And what was nice was that there were already papers comparing existing methods which use data for this exact data set. So I think the variables are, again, something only domain experts will understand. It's something like cloud water path, net shortwave and longwave flux, etc. But we do the same thing. We just give this variable names to the LLM and ask it to tell us which way the direction goes, or there's no graph, or there's no edge. So you look at these methods. I think one of them is TCDF. It's a temporal method. It's data-based. No tiers is this deep learning method that I was just describing. And DAG-GNN is a graph neural network method. All of these are very recently proposed, close to state-of-the-art methods. And the metric they were looking at was NHD, which you can think of it like structural Hamming distance. It's essentially saying how many edges you got from. If you had the true graph and you compare the predicted graph, how many edges were in there? So when we try GPT 3.5 Turbo, we get almost the same NHD. That's interesting. It kind of means we are at the same level. But again, the latest model, GPT-4, gets it lower to about 0.22, which is quite interesting, I mean, because it's not even looking at the data at all. What it's telling you is that there is some interesting complementarity, like people have been just ignoring the names of variables or the metadata that they had, and for right reasons, because you didn't know anything, what will you do with them, right? But now we have models which can make sense of those metadata, and so you should use them. And the open question then is, how do you combine these two methods? Another question. So now let's come to this memorization, right? How do you test whether the LLM is really reasoning, generalizing, or it's just essentially a database. It's just memorizing things and then giving them back. So we did this interesting experiment where we asked a different question to the LLM. We'll give it a part of this data set, which is the Tubingen data set, which is available online, and we'll ask it to complete the rows of this data set. Okay, so it's a very different task. But if the LLM can complete the rows of the data set that we are testing it on, then that probably means it has memorized it. Right? Because now this is not about causality. This is just about, hey, here is the data set. I'm giving you a README, and I'm going to give you partially the row. Right? And the right answer should be like age, length, and then which direction the edge goes. What we found was that if you look at GPT-4, it can complete about 25% of the rows correctly. That's quite something. And it can also complete about 61% of the cells completely, which means that what's the next word? Like, can it predict the next word correctly? So this clearly shows that this Tubingen data set was in the training set. Otherwise, it's very unlikely that the LLM would even know what this means and what needs to be added in the exact format of this data. And so in a probabilistic way, you can think of
the previous test. I think the sampling technique matters because high temperature you might get a different answer.
Oh yeah, so I think we just tried zero temperature, if I remember correctly. We did not do any kind of variance estimations. But in any case, 25% is a big number, right? That you would agree. It should have been not. And so one way of thinking about it probabilistically is that there are these two kinds of probabilities, right? There's one which is probability of D, which is that this data or this question that you're asking is already in the training set. The other is you're conditioned that this is in the training set. Can the LLM give me the right answer? So I think the first one is more like a training data set challenge, which is very hard to estimate. Who knows, right? These companies won't disclose you. But what we understand is that this is what our experiments at least are measuring, which is probability of Y given D. So even if you assume the worst case and assume that D is your question is already in the training set, how well can LLMs understand English and give you the right answer in the specified format? So that's the conservative interpretation. If you write this interpretation, you can sleep at night and be happy that LLMs are just databases. They're not doing much, but they just have a lot of data. Right? But I think, personally, this is what's going on. Some of it is memorization, but I think there's also some generalization happening, which we don't fully understand. So, of course, for memorized things, it's doing well, but it's also doing well for medical and these Arctic science datasets, which were very rare, sort of less popular datasets. And then it's also doing well on slightly out of distribution things that we are trying anecdotally. So we don't have scientific evidence, just anecdotally, we can also try it. And you will find traces of some reasoning. It's just not clear how it's achieving it. So let's I'll just quickly give you the recap for this session, and then we can break for about 15 minutes. So if you're interested in causal inference, just a quick bonus, LLMs can do many other things which only people could do. So for example, if you give it a causal study, it can suggest you what confounders you might have missed. If you ask it to suggest an instrumental variable or suggest how to validate a causal study, it can also do that. And if you're interested, you can try out this repo that we have created. It's on GitHub, open source, called pairwise. You can actually just give any data set and do these kinds of things where you can ask, hey, suggest me some confounders, or modelers suggest relationships that might exist in my data. Here's a quick example, just to show that this is not just about causal discovery. It's about a lot of tasks that people thought would be very hard for machines.
Just to changing prompts actually changes the accuracy.
Yeah.
Suggested file is doing something wrong.
Yes, that is another way of looking at it. Yes, that is true.
So if it's just the database, it won't have changed.
Yes. And also it changes on how you describe things, right? So it can pick up the fine variations in meaning. So one thing I can say, it is beyond doubt now that it can understand these concepts. I think a lot of people agree that even the hard kind of astrophysics or medical concepts, if you ask it what it means, it gives you the right answer. I think now what's not clear is how does it also understand the relationships between those concepts. Because not all of that might be written down in text. Right? That's not how internet text is. So somehow it is able to, maybe transitively it can reason. So maybe A given B, A causes B is written, B causes C is written, and it's able to also transitively make sense. So here's another example. Actually, this might actually whet your curiosity even more. So here, these are kinds of examples we were trying to fool the model, to be honest with you, right? So this was not in the part of the paper. We were just thinking, okay, what is it that you can do to fool the model? So we gave it this data, right? So a toy shop owner in the Western US has some toys, and they found that in December, their sales increased a lot. And they now want to do what to do in February. Can you help them decide what's the increase in sales due to the ad or not? So if you're in the US, then if you know about Christmas, you would realize a lot of people share gifts about toys during December. So maybe that's the reason, right? And we prompted the LLM ask, like, what confounders do you think might exist, which can affect the estimate? And if you look at the answers, I think they're almost what you might get from some statistician or some kind of expert who spends their time thinking about causal inference. So the first thing it says is it gets the right answer, seasonal variation. I mean, December is the time that people buy things, so it might be there. But then it also gives other things which I had not thought about. Like there might be more inventory, there might be competitive landscape, there might be some marketing going on outside of your ad, which you did not check, and so on. So all of this is to show like if you are interested in studies like these, then you can almost use the LLM like a brainstorming tool. It's going to be wrong, it's going to give you crazy things, but it's a nice brainstorming tool for you to make sure that you've covered all the variables. And so implications for research, as Siddharth pointed out, are today about how do you combine these methods. So interestingly, the field moves so fast, there are already 2 or 3 papers that are trying to do that. So I've listed them here. So one paper is trying to reduce the size of Markov equivalence graphs using LLMs. The other paper says that let's just use them as priors. So we'll get a Bayesian prior from these LLMs. They have a way of getting confidence scores. And then we can just use any score-based algorithm and score all the graphs. But I think there are 2 questions which are still, I mean, these are early papers. I don't think they have solved the problem. So one is how do you get a confidence score from an array? All the answers that I showed you just give you, oh, here's the answer A, here's the answer B. And LLMs are not good at giving you a proper probability score or a proper confidence interval for their answer. So I think this kind of is a very important question because the moment you want to use LLMs in any probabilistic tool, you would want some kind of probabilities to come out. And the second open question, I think, which again people are starting, is that if this is true for causal discovery, can we scale it up to downstream tasks? So if we just want to do prediction, if we just want to do effect inference, or if we just want to attribute failures in some system, can you have a system where the LLM is the first agent that gives you some prior, and then you also have a decision made kind of automatically without any human involvement, at least minimal? So I think this part, I believe a lot of work will happen empirically. People will just try to build systems using LLMs. Yeah.
Do you think like your claims on being able to discover causal effects between pairs have implications for reasoning? So, for example, a logical reasoning statement A can imply B or not.
Yeah.
So, and if you give it 4 options B, C, D, E, you might be able to find the reasoning.
That's the second part of the talk. Yes, that is the second part of the talk. We'll exactly study those things. Yeah, I think that, as I mentioned, there are implications of practitioners as well. So if you are familiar with Tubingen and EconoML, we're kind of trying to integrate LLMs in those libraries so that people can also try out these kinds of functionality. And if I had to summarize 3 takeaways, I think the first is that LLMs are enabling a new kind of knowledge discovery. And it's very exciting because database causal discovery was kind of hitting a peak. And it was hard to kind of think of what will take this to the next level. So there is a lot of delta now that we can explore to combine database with knowledge-based discovery algorithms. There's also this very interesting question of memorization. Like if someone can figure out good tests to check how much is in distribution, what is out of distribution, and have some way of evaluating the true reasoning of these models, I think that's a very important open question today. And then also, for example, you can also think of just the downstream tasks. Right? How do you just improve the robustness of an effect estimation method? Or how do you improve the robustness of any kind of decision-making system using these kinds of tools? So with that, yeah, I think we can take a break and we can come back to the second part where I will talk about not graphs. I know a lot of people don't care about graphs. I'll talk about real-world questions that people have and whether LLMs can answer them and whether they can even attribute causes as necessary or sufficient just based on some English description of the task. I'll stop.